You may have been doing some work with Newton's laws of motion. That's great. Let's just take that one step further and talk about momentum. Momentum is a term which refers to the quantity of motion that an object has. So let's start with an object. Here's an object. At the moment, it might be moving, it might be at rest. Who's to say? But let's make it an object in motion. There we go. We've got some speed marks on. That object is now obviously moving over to the right. So it's an object in motion. That's grand. This object now has momentum. Momentum is defined as mass in motion. And since all objects have mass, then if it's moving, it has momentum. Now the amount of momentum that an object has depends upon two variables: how much stuff is moving, so its mass, and also how fast the stuff is moving, so its velocity. So momentum depends upon the variables mass and velocity. In terms of an equation for momentum, well, we have the symbol p, a lowercase p for momentum, and momentum is equal to the product of the object's mass and the object's velocity. Now, momentum is directly proportional to an object's mass, as we can see from this equation, and it's also directly proportional to the object's velocity. What does this mean? Well, directly means that as one variable changes, the other one changes in the same direction, and proportional by the same factor. So if, for instance, the mass doubled, but the velocity remained the same, the momentum will also double. So the mass went up, the momentum also goes up. Mass went up by a factor of 2, the momentum also goes up by a factor of 2. Okay, so momentum and mass are directly proportional. Momentum and velocity are also directly proportional. Now, the unit of mass is, of course, the kilogram, and the unit for velocity is meters per second, and that gives us now the unit for momentum. The units for momentum are the kilogram meter per second. You might also see it written like this: kilogram meter per second. But remember that s to the minus 1 simply means that s is down on the bottom line. Now, another thing we should say about momentum is that it is a vector. Remember, momentum is the product of mass and velocity. Well, velocity is a vector, and if velocity is a vector, that is going to make momentum also a vector. This means that direction is required. It's not enough to say that momentum is equal to 10. Okay, so there's our number, and then we put the units, kilogram meters per second. There we go. That's the momentum. Well, actually, no, it's not. We would need to give some sort of direction. We might say the momentum is 10 kilogram meters per second west, or some other direction. Okay, it doesn't really matter what the direction is in this case. I'm just pointing out that we have to state a direction because momentum is a vector. Now, here is a skateboard, and here is a truck. It looks kind of more like a bus. Okay, let's call it a bus. And buses' wheels don't look like that. But anyway, there's a skateboard and there's a bus. Both mass and velocity are equally important in determining the momentum of an object. We know this because momentum is equal to the mass times the velocity. They're both important. So if a bus and a skateboard are moving down a street at the same speed, let's do that. Let's put the bus in front. It's moving that way at 5 meters per second. And the skateboard, same speed, so 5 meters per second. The bus has a much greater mass, obviously, so it also has a much greater momentum. Okay, so momentum does depend on the mass. The bus has more mass, and I've just realized the bus is going backwards, but that's okay, the bus is in reverse. The bus has more mass, so it has a greater momentum. But if the bus were at rest, if it were not actually moving anywhere at all, well, now actually the skateboard has the greatest momentum. Because remember, momentum is the mass times the velocity, and if the velocity is 0, if the object is at rest, well, then the momentum is going to be 0. So that bus right now at rest has no momentum, so the skateboard actually, in this case, has more momentum than the bus. So the momentum of any object which is at rest is 0. Now, hopefully, because of this, we can see a key difference between momentum and inertia. Okay, inertia still applies if an object is at rest. It's inertia that tries to keep that object at rest, right? And if the object is moving, inertia tries to keep that object in constant motion. That's Newton's first law of motion. However, with momentum, if the object is at rest, momentum is zero. It doesn't have any. Only when the mass is moving, has some velocity, then we have momentum. So let's now just look at doing a couple of quick calculations involving momentum. Here we have a 65 kilogram halfback, so they're playing a game of rugby and he's moving east at 9 meters per second. Well, remember the steps that we go through when we're doing these physics calculations. First, we start with an equation. Now, our equation is simply the momentum equation. There we go. Momentum equals mass times velocity. And then we rearrange if we need to, which obviously in this case we don't. We're looking for the momentum. And then we put the numbers in. So mass is 65, velocity is 9, and then we reach for our calculator and we get the answer. And hopefully you should come up with the answer of 585. And then, of course, we put units on. We're talking momentum. Our units are kilogram meters per second. And then we would show our rounding if there had been any, but I didn't round it all, so there's the answer. That halfback has a momentum of 585 kilogram meters per second. But wait, that's not the answer, is it? That's not the full units. Remember, momentum is a vector. We need to show the direction. So the question gave us the direction. It was east, so we need to say east. That is now the answer. So it is important not to forget the direction because momentum is a vector. Let's look at another one. We have the equation, mass times velocity. We know we're not rearranging, so we have 1,000 kilogram, a 1-ton car moving at 20 meters per second, and we shouldn't even need to reach for our calculator for this one, 20,000, and then we have the units, kilogram, kilogram meters per second, and it is a vector, so we state the direction which we were given in the question. So there we go, that car is moving with a momentum of 20,000 kilogram meters per second south. One more example, just to make sure we've got the hang of this. Momentum equals mass times velocity equals 55 kilograms times 2 meters per second, and that gives us a momentum of 110 kilogram meters per second north, because that's the direction the student is moving. So there we go, a couple of quick examples of momentum calculations. Let's now add a new term into the mix. This new term is impulse. To stop an object moving, remember we had that object moving at the start. There we go, object moving along. To stop that object moving, you would need to apply a force against its motion for a given period of time, right? So we want to change its motion. We know that we need to apply a force onto that mass, and that will give us acceleration. We know this from Newton's second law of motion. So we want to accelerate the object. In this case, we want to stop it. So that's a change of motion. That's acceleration, right? It will be slowing down, which is negative acceleration. So we need to apply a force for a given period of time. Essentially, the force is not going to be an instantaneous force. It's going to be applied over a time frame. Now, if an object has more momentum, and it could have had more mass, so there we go. If we up the mass, we're upping the momentum. If the object has more momentum, it's going to require a greater amount of force or a longer amount of time, or both, to bring it to a halt. Okay? Now, since a resultant force acts upon the object for a given amount of time, the object is accelerated according to this second law of motion here. But of course, acceleration is the change of velocity over time, right? This little a here is the change of velocity over time. Delta, that little triangle, that is the Greek symbol delta, and it means change. Okay, so anytime you see a triangle like that in your equation, it means change of this thing. So this F equals ma could be rewritten as mass times the acceleration, but acceleration is the change of velocity per time. So there we go. Force equals the mass times the change of velocity over time. Well, let's grab that time. So therefore, and we'll take the time across the equals. When we do that, we have to do the opposite. So instead of being divided by, it's going to be multiplied by. So now we have Ft, force times time, is equal to the mass times the change of velocity. Here is a new equation for us. Let's look at this one right here. Ft equals m delta v. Ft is known as the impulse. Now, that screen's starting to get a little bit full, so let's just go to a blank one. I'll write that again. Ft equals the mass times the change of velocity. Now, Ft is known as the impulse. Okay, so we've covered momentum. Now here's a new concept of impulse. And because we had that momentum was the mass times the velocity, well, that means that mass times the change of velocity must be the change of momentum. So what the equation at the top really says is that impulse equals the change in momentum. And the units for impulse, well, being force times time, the units are the Newton second. Right? We get that from the force times time. So there's our new idea, this idea of impulse. The units are Newton second, it's force times time, and it's equal to the change of momentum, mass times the change of velocity. So impulse equals change of momentum. The physics of collisions are governed by the laws of momentum. Let's consider the case of a tennis ball slamming into a wall and bouncing off. Actually, let's consider two cases, case A and B. So has a brick wall. There we go. And case B also has a brick wall. Grand. Okay, case A. Let's say the tennis ball is inbound to the wall with a velocity of 10 meters per second, and it hits the wall and it bounces off with a velocity of 5 meters per second. In case B, the tennis player hit the ball rather hard, and the ball had an inbound velocity of 30 meters per second, and it bounced off with a velocity of 28 meters per second. Okay, so it's the same tennis ball, so the mass doesn't change at all. Now, the first question is, which case A or B, shows the greatest change of velocity? Right, so which one had the greatest change of velocity? Well, you might look at this and say, well, A, because the change of velocity is 5, and in B, the change of velocity was only 2, right? 30 take away 28 is 2. So case A obviously had the greater change of velocity. You would, of course, be wrong, because remember, velocity is a vector. Direction is important, all right? It didn't just go from 10 to 5. It went from 10 to the right to 5 to the left. So we've had a change of velocity, which is negative because the ball changed direction. So let's just write case A. Change of velocity is going to be negative because the ball turned around and went the other way. And the difference is, well, from 10 that way to 5 this way, the difference must actually be 15 meters per second. So there's our change of velocity of negative 15 meters per second. What about in case B? Applying the same logic, it's not just the difference from 30 to 28. It's from 30 to the right to 28 to the left. So the change of velocity, again, negative, because the ball turned around. And the change of velocity is now actually 58, well, minus 58 meters per second. So actually, case B showed the greater change of velocity. Okay, great. Let's talk about the greatest acceleration. Which case showed the greatest acceleration? Well, that's also B, isn't it? Because acceleration is change of velocity, right? So we've just worked out the change of velocity, and B had the greater change of velocity, therefore B has the greatest acceleration. You might also be asked, all right, which case shows the greatest momentum change? Well, once again, that's situation B, case B. Remember, the change of momentum depends on the change of velocity, which we've already said was case B. So case B, because it had a greater change of velocity, it also had the greater change of momentum. And of course, change of momentum is equal to impulse. So when part D of a question says, okay, so now which had the greatest impulse? Well, case B had the greatest impulse because it had the greatest change in momentum. And it had the greatest change in momentum because it had the greatest change of velocity. And because it had the greatest change of velocity, that means it also had the greatest acceleration. So yeah, all of these questions, case B is the answer. What you need to remember is that that velocity that we started with, it is a vector. So we can't just look at the difference between from 10 to 5 and from 30 to 28. You have to consider the direction as well. So we actually had a change of minus 15 and minus 58. Now, the last thing we'll just take a quick look at is the effect of collision time. So an object with 100 units, say of momentum, must experience 100 units of impulse to be brought to a stop, right? But any combination of force and time, the impulse, right, force and time, any combination of those two could be used to produce the 100 units of impulse necessary to stop the object. Let's just draw up a quick diagram of this, well, a table rather. So force in newtons, we have time in seconds, and we have impulse. And the units, of course, are Newton seconds for impulse. So we've got 100 units of momentum, and we want to stop that. Okay, so a force is going to apply over a time. We want to stop this object. So what could happen is, well, we could apply 100 newtons of force over 1 second, and that would give us our 100 units of impulse needed to stop the 100 units of momentum. Okay, or maybe we didn't supply 100 newtons of force. Maybe we only supplied 50 newtons of force, but we could supply that force over a time of 2 seconds, and that would also give us the 100 units of impulse needed to stop that 100 units of momentum. Or maybe we just supplied 4 newtons of force, but we supplied that force over 25 seconds. Once again, 100 units of impulse needed to stop the 100 units of momentum. Maybe we supplied a teeny tiny bit of force, just 0.1 of a newton, but if we applied that force over 1,000 seconds, well, you guessed it, we're getting the same impulse required to stop the object's momentum. So we can see from this that the greater the time over which the collision actually occurs, the smaller the force acting upon the object. Therefore, to minimize the effect of a force, we just need to increase the time. Or if we wanted to maximize the effect of a force on an object, we would decrease the time. Think about catching a ball. If a small ball, a small hard ball, maybe a cricket ball or a baseball, something like that, if that's flying towards you and you stick out your hand, and when the ball slams into your hand, if you don't move your hand, that's a lot of force over a very short time frame. If, on the other hand, you actually move your hand with the motion of the ball as you catch it, what you're effectively doing is extending the time of the collision, and so that decreases the force. Okay, so like we see here, we extended the time to 25 and our force came down to 4 newtons. If we extended the time of the collision to 1,000 seconds, the force came down to 0.1 newtons. So if we extend the time frame of the collision, we can decrease the force, and that won't hurt our hand.
Evan, there's been a lot of changes this offseason for your team. How do you feel your chances are in the AL East?
I mean, I love our chances. It's been... Man, guys, keep it on the field. Man, guys, keep it on the field.
So there you go, momentum and impulse and a bit of collision work in there as well.
Like the video, punch that like button. Want to see more videos? Smash that subscribe.